Hello, everyone, and thank you. Welcome to phyloseminar.org. The current theme is phylogenetic networks, which generalize trees by allowing loops in the graph. In this series of 3 talks, we are hearing 3 perspectives on networks. First, we heard from Luai Nakle on statistical inference of phylogenetic networks from multi-locus data. Then we heard from Celine Skornavaca on parsimony methods. Today, Cécile N.A. will describe challenges in network inferences, as well as how one can use networks in phylogenetic comparative methods. I want to remind people that the Q&A app is gone now, so you can ask questions through Twitter or IRC as described in the attending section of the phyloseminar website. As I mentioned, today's speaker is Cécile N.A. Cécile is originally from France, where she did her BS and MS in math, then a PhD in probability, graduating in 2000. I think we'll be able to see this background in the material she'll be presenting today. Since then, she has been at Wisconsin-Madison, joint between this departments of statistics and botany. Welcome, Cécile, and thanks for participating.
Yeah, thank you so much, Eric. So it's a pleasure to be part of this phyloseminar series on networks. Thank you so much for the opportunity. So to end the series, I wanted to talk about 3 topics. One is just come back to the basic question of why should we bother? So phylogenetics is about studying the evolutionary history of a group of species. And trees are very natural for this. They're very convenient. So why should we bother about networks? So I'll talk about danger of ignoring reticulation first. And then I'll talk about challenges that come with networks that are somewhat new to networks, or at least more difficult in networks than in trees. And then finally, I'll talk about really what I'm getting excited about these days is using networks for the study of trait evolution. So, oh yeah, and Eric, I wanted to say, feel free to interrupt me anytime if you catch any question on Twitter or on our IRC, because I'm really happy to answer questions before the end of the talk.
Sounds great.
Yeah. So dangers. Here I'm going back to 10 years ago when we were mostly doing concatenation of different genes. And then we wondered if incomplete lineage sorting might have an impact on tree reconstruction. So incomplete lineage sorting, just to remind people if they haven't seen Luai's talk, it's a process that is within populations and that can happen during every ancestral population in a species tree. So if here we have 2 alleles, one coming from A, one coming from B, they need a few generations to have a common ancestor. And so most of the time, they do have a common ancestor before the lineage here, the ancestral population merges with another. But for some small probability, some proportion of genes, this is not going to happen. There's not enough generations. And that can lead the lineage coming from species B here to have a common ancestor with C before it does have a common ancestor with A. So that's called incomplete lineage sorting. And about 10 years ago, we wondered, oh, is that a problem? And the answer from a famous paper by Laura Kubatko and James Dagnon was, yeah, it does matter. In some cases, concatenation is not robust to incomplete lineage sorting. We can get a tree with super high support, but it's a wrong tree. And the background reason for this was that there are anomalous gene trees. So I will come back on this later. But that really led to the development of a bunch of new methods that are based on the coalescent model to model incomplete lineage sorting. And several of them, like Astral and SVD Quartet, use sets of 4 taxa because there are no anomalous gene trees on 4 taxa. So now that was 10 years ago. And now we're interested in gene flow introgression and networks. And so this network would represent 4 taxa. And here there could be a gene flow between the ancestral D population to the ancestral C population. So if we think of modern humans, for example, the gamma value, so that's represents the percentage of genes that were passed from D into C. So if we think about modern humans and Neanderthals, so humans from European and Asian ancestry got about 2% genes from Neanderthals. So that, in sometimes it's small. If we think of C as a hybrid species, that would be a lot higher. But even, small gene flow, we can wonder, does that affect our tree building methods? So this would mean, this network would mean that most of the genes, like percentage 98% in the example I used, would have this topology, and a small proportion of genes would have the alternate topology, like 2% of the genes would have CD as sister instead. So we can ask the question, and then the answer, unfortunately, is that yes, there is an impact. It does matter. So some coalescence-based methods are not robust to gene flow, and so that's something I worked on recently. So I wanted to show a little bit what we did, because we found that there are anomalous gene trees, and really we focused on unrooted gene trees. So this is a network, unrooted network. But if we think about D being an outgroup, then C is sister to AB. And so this gene flow in red would represent gene flow between sister species. And so we can wonder, if there is this gene flow, does that affect our best methods that account for the coalescence process? So looking at gene trees, we would expect gene trees to have A be a sister, because regardless of this red arrow or the backbone gene tree, A, B are sister to each other. So we would want A, B to come up as a sister in the majority of the genes. And it is the case if there's no gene flow. So no gene flow corresponds to gamma equals 0. And here is the theoretical proportion of genes that where A, B group with each other. So that's roughly 35% in an example where the branch lengths T1 and T2 are very short, meaning very closely related species that speciated rapidly. And the alternative gene trees where, let's say, C is sister to A, so C sister to A here, or C sister to B, they would come up with a lower frequency, like 32%, 33%. So that's all good, because AB appears in more gene trees than A with C or B with C. But when we put some gene flow, like here 10%, then this pattern is reversed, and we have fewer gene trees, here just 30%, where A, B group with each other, and more gene trees where A and C group with each other, or C with B group with each other. So these two gene trees, C with A and C with B, would be called anomalous, because they are too frequent, more frequent than what we expect, so than the gene tree that we see in the species tree. And this is really severe if we have, say, 30% of heritability, inheritance for the gene flow events, where A and B are grouped with each other only 26% of the genes, and it's either C with A or C with B in 37%. So that could be quite severe, and that is a problem for the species tree methods that assume that on 4 taxa there are no anomalous gene trees, and we do get anomalous gene trees when there are gene flow. So we looked at various methods and see how they're impacted by gene flow. We looked at concatenation, and then we looked, which we don't expect to be consistent if there is strong incomplete lineage sorting. And we looked at astral and NJ species tree. A slightly larger network than just 4 taxa. But we have the same pattern where taxa 3 and 4, we would want them to come as sister in the tree that we infer from data. And what we so they come up as sister in the white area, right? They don't come up as sister in the green, light green area, or dark green area. And what we see, if there is only a little bit of gene flow, I mean up to 10%, here concatenation doesn't do well, because with more and more genes, the white area becomes smaller and smaller, so we don't recover 3 and 4 sister. But Astral and NJ species tree, never joining species tree, it's still an area where they do well, because with more and more genes, the white area becomes wider, and they tend, eventually they recover 3 and 4 sister to each other. But if there is more gene flow, that here it's gamma is 0.3, then they're misled, more and more data, and then the white area vanishes, and instead they recover 3 and 4 not sister with each other. Either they get 3 and 5 sister, or a 4 and 5 sister to each other. So that's a concern. That's a reason why we should worry about reticulation. Even if it's not the main goal of the study, we should pay attention to it. So the next question is, okay, I have a data set. Am I in an area where tree methods are going to be misled? Do I need to worry about reticulation? Even if it's not my primary interest, do I need to worry about it? So this is some work I've done earlier, actually, to get a test to see if a tree and the coalescent model, is that sufficient to explain our data. So it's basically a goodness of fit test, where we have a tree, we know what we expect from the tree. So in this cartoon, we have set 4 taxa A, B, C, D. We have some branch length on the internal edge. And this branch length in coalescent units tells us what I should expect. And I should expect, let's say, if it's 1.2 coalescent units, I should expect 90% of the genes to have A, B sister. And then the remaining 2 conflicting options, let's say C with A or D with A, they should each have an equal proportion in the set of genes, here 10% and 10%. So it's exactly, this test uses exactly the same idea as the ABA-BABA test that uses SNPs. And the idea is that these 2 proportions, it should be equal. So we should see the same proportion of genes with this pattern as the proportion of genes in that pattern. What our test does is it combines all sets of 4 taxa to do a single test. And so we can get to see if the tree is a good explanation, and we can stop there, or if we need to go and worry about reticulation. So next, I'd like to talk about new challenges with networks. So now that we worry about reticulation, what are new problems? One problem, I talk about network thinking, because tree thinking is not obvious. Network thinking doesn't get easier. And then I talk about computational problems, and then more theoretical problem of, do we have enough information to identify the network? And then a really practical problem about visualizing uncertainty in our network reconstruction. Right. So first, network thinking. The issue here is that when we have a network, say this network, there's not one sister. So if we take this group here that's underlined with dark blue, this group, we can feel good about calling this a clade. But then there's not one sister. And we're really used to saying, this is the sister of that clade. That's the sister of this other clade. And here we have really 2 sisters. If the inheritance values are 80% here, 20% here, it's tempting to call this group the major sister, because for 80% of the genome, it is the sister. So for a majority of the genome, that's the sister clade. But there is this other alternative group that is sister for 20% of the genes. So it's like we have recomposed families, have siblings. That makes things just more complicated to describe. And even just the clade concept gets fuzzy. So we can be comfortable calling this group in dark blue as a clade, but how about this light blue group? Is that a clade? For some genes, yes. Well, if we ignore incomplete lineage sorting, right? But should we call this a clade? You know, and maybe if these inheritance values are, you know, this one is small, let's say just 2%, and this is 98%. You know, we could feel comfortable about calling this light green group a clade. But if this is a hybrid and these inheritance values are, let's say, 45%, 55%, we would feel less comfortable calling this group a clade. So if we don't have clades, things are getting more difficult. Classification is definitely getting more difficult. So something that helps is to remove from the network all the reticulation edges that have here an inheritance probability less than 0.05, to consider at each reticulation point what is the major relationship that is followed by a majority of the genes. So we would drop this red arrow, we would drop this other red arrow, and then we would get a tree. And I call this the major tree because it's true for, at each node, it's true for a majority of the genome. But should we call this a species tree? You know, what does a species tree mean anyway? So just network thinking is more difficult, and that's why we tend to prefer trees. And if we can ignore reticulation, we're really glad to do it. And then we have computational issues. So here, just going to talk a little bit about the network coalescence that Louai talked about, and Céline recalled also. So this model would have the coalescence model on each branch of the network. On this ancestral branch, for example, we would have we need a branch length, for example, in coalescent units, to model incomplete lineage sorting. And then the topology would be a network with some nodes, here this internal node, be hybrid nodes with two parents. So each time we have two parents, we need inheritance probabilities to say how many genes were inherited from this parent and how many genes were inherited from that parent. And that's what we use in an independent way for each lineage that reach a hybrid node. So this is really not new. It was first described by Meng and Kubatko in 2009, and then extended to general cases by Yu, Degnan, and Maclay. So it's great to have this model, and then we can have data and fit the model to the data to infer a network. So typically data are multiple gene alignments, and we can get the likelihood of these alignments directly. It's really hard. Or go by getting a gene tree for each gene alignment, and then use the gene trees as input to calculate the likelihood of the network. But this is really hard. A great improvement was done in 2014 to have a very smart algorithm to calculate the likelihood of the network given gene trees, a lot faster than it used to be. But this is really still very complex. And the best maximum likelihood method that is implemented in PhyloNet can be applied up to 10 species, up to 3 or 4 hybridizations, but it's hard to make it work for more complex problems just because it takes a very long time. So we will need better ways to do this in the future. What this maximum likelihood approach requires is rooted gene trees, and one version uses branch lengths, another version does not use branch lengths. So I want to talk about these two assumptions, that we have rooted gene trees and that we can use branch lengths, because I think it's important to talk about, to consider these questions. So should we use branch lengths in gene trees? I think it is a dangerous assumption. Typically, this is some. No, what I mean is, I think it's dangerous to use branch lengths in gene trees, because typically the assumptions that are made are that all genes evolve at the same rate, and we know that that's just not true. There are genes that evolve faster or slower. So there can be ad hoc ways to rescale the gene trees, but still it's ad hoc. And then another assumption that's typically made is that for each gene, all their lineages evolve at the same rate. So some kind of molecular clock assumption. Some methods do relax, because we don't have to have the species tree be ultrametric. So that would allow for some departure from the molecular clock. But then this departure is typically assumed to be the same across all genes. And we know that a departure from the molecular clock is just different for different genes. When we calibrate trees using BEAST, we definitely don't make this assumption. So all I'm saying is that typically when we use branch lengths, we are making dangerous assumptions. That is not true for Bayesian methods that can relax these assumptions using very few parameters. But still, for the most part, it's just dangerous. And then if we go back to species tree methods, so think about Astral, for example, the methods that ignore branch lengths, there's been a lot of studies showing that they're more robust. Yeah, so I think we will find in future studies that it is probably the same for networks, that we can do pretty well without using branch lengths in gene trees. Yeah. So another question is, should we use rooted or unrooted gene trees? Typically, methods use rooted gene trees. And here, again, I'm concerned, because I think there's a danger in rooting all gene trees with an outgroup. So if we choose an outgroup, so let's say in orange you have the in-group, and then in red you have the outgroup. If we choose an outgroup that is closely related to the in-group, then there is a danger of the outgroup being involved in incomplete lineage sorting with the in-group. And so if we pick the red edge for the gene tree to put the root of the gene tree, we would be making an error. So if we want to avoid this, then we can pick an outgroup that's further away, so not as closely related. And then there is another danger, is that branch lengths can be too long. The branch lengths to the outgroup could be too long. So here there could be saturation. And if branches are really too long, there could be long branch attraction issues. So there's probably a sweet spot in between. But on either end, it is dangerous. And I want to recall this paper from John Gatesy and others in 2007, where they showed that in a really famous yeast data set from Rokas et al. In 2003, almost all of the incongruence could be explained by routing errors, with three outgroups that were really too far from the in-group. And then the problem is that we tend to use lots of gene trees, and it makes it difficult to check the root of all of them. So if we make a blanket assumption, I think that's dangerous. So these considerations led me to look for another method that would use unrooted gene trees, and that would not make any use of branch lengths to avoid assumptions. And so that's why I developed SNAC, a species network, using quartets. So quartets are sets of 4 taxa, and if we consider gene trees on quartets unrooted, there are 4 options. So we can use a data set of multiple genes and then summarize all these the relationships across genes using a summary on each set of 4 taxa. So the summary could look like a table like this here, where we list all possible sets of 4 taxa. And for each set of 4 taxa, we can calculate the proportion of genes that have taxon 1 and 2 grouping together, proportion of genes that have taxa 1 and 3 grouping together, and then the third number would be proportion of genes grouping taxa 1 and 4. And to get this, it's best to integrate over tree uncertainty. That's possible using Bucky. And then, once we have a summary of the data set like this, then we can do a likelihood of the summary. So we can have the likelihood of, for these 4 taxa, the likelihood for the next set of 4 taxa, and then combine all of this with a pseudo likelihood approach and infer a network. So that's what we worked on some time ago, and we called SNAC. The advantage to using sets of 4 taxa is that calculating the likelihood of one set of 4 taxa, it's fast. So granted, there are many sets of 4 taxa, so we have to repeat this many times, but each calculation is very fast, so it makes the method scale to a bit larger data sets. The next challenge is to know whether we have enough information in whatever data set we're using. So Céline talked about using branch lengths, and with Fabio Pardi and Céline, they have a really, really nice paper looking at what information we can get about the network if we're using gene trees that have branch lengths. And in their model, they didn't have ILS, but they showed, even with this, in a way, it's an easier setting if there is no incomplete lineage sorting. Even in this easier setting, we can only estimate, identify a canonical version of the network. So the full network cannot be identified. Its canonical version can be. Then we can ask, okay, now if we use a coalescent model, what can we identify from the network if we are using rooted gene trees? And I don't think there is an answer right now in the literature, a detailed answer to this. So we can try, but if we find areas of flat likelihood, it means that maybe we don't have enough information about the network from just using gene trees. And then when we worked on using quartets, unrooted quartets, we looked at this question. And so we asked, okay, what can we identify from the network? And one thing that we cannot identify is the roots. So it seems logical that if we use gene trees are not rooted, then we cannot infer the roots of the network, and that's the case. So that's okay, we can infer an unrooted version of the network, and then use an R group like we do for species trees. Can we identify the gene flow placements and the direction of gene flow? The answer is yes and no. So no if we only have 4 taxa, but if we have more, then yes, we can. So that's really mirroring the results from the ABA-BABA test, where 4 taxa, we can tell if there's gene flow, but we cannot really tell the direction or where it comes from, where it goes to. And then the default test is an extension of the ABA-BABA test to 5 taxa. And they showed the same thing, that some gene flows they can detect and identify, and others across 4 taxa, they're not identifiable. So we find the same thing when we use unrooted quartets, which makes sense.
You're begging a question when you say for most networks.
Oh, that depends where. Yeah, it depends where the hybridization is placed. So if it really depends on the cycle that is created by the hybridization and how many taxa are attached. So can I go, let me show you this. So here, for example, we can identify these 2 networks and we can tell the direction of the gene flow. But in some cases, it's not possible. If here the cycle involves 1 node, 2 nodes, 3, 4 nodes. So on these cycles that involve 4 nodes, we can identify. But if the cycle involves only 3 nodes, then we cannot. I don't know if that answers your question. I guess so.
Yeah, absolutely. So it's maybe this is related to the fact that you can't infer the 4 taxon case, that it's sort of there's not somehow enough information in the smaller reticulation.
Yeah, it also that's true. It also depends on. So these are on other networks where there are 4 nodes. It also depends on how many taxa are attached to each of the 4 clades, if you want. Yeah, so it's complex. It's not an easy question, and
cool.
that's why we don't know much about this. Yeah. So another question is, can we identify the branch lengths? All these numbers that we want to put in the network. And some of them, yes, and others, no. It's again, it's a complex answer. Yeah. I would expect more papers on this later. So another challenge, really practical here, is how do we summarize uncertainty? On trees, it's fairly easy because one edge, we can cut an edge on a tree, and that cuts the set of taxa into 2 sets of taxa, so by partition. It partitions the taxa into 2 sets. So we can compare edges across trees by comparing the taxa that are on either side of the edge. But on networks, that's not true. So if, let's say we take this edge, and I cut this edge, I'm not separating all taxa. They're still connected by the other edges. So an edge does not correspond to a bipartition in a network. There's not an easy correspondence of edges between networks like there is for trees. So, so how do we calculate edge support? So our approach to this is to simplify the network by removing the minor hybrid edges. So this hybrid node here has 2 parent edges. One would have a gamma inheritance less than 0.5, and another would be used by a majority of the genes, more than 50%. So we could delete this edge, the minor edge, and say, okay, now if we delete this edge, we have a tree. And then now when we have a tree, then any other edge would correspond to a bipartition. So the first thing we can do, if we have a set of bootstrap network, or we have a set of posterior sample of networks, and we want to summarize this full, big set of networks, is remove all these minor edges from all networks, and then we get our major trees, and then do the usual thing we do on trees to get bootstrap support or posterior probabilities of edges. So this is an example below where I had a set of 100 bootstrap networks. When I removed all the minor hybrid edges, I got 100 bootstrap trees, and all these trees were the same. So they all had 100% bootstrap support for clade AB, 100% bootstrap support for clade CD, 100% bootstrap support for ABC, or same as OE together. And then the next step is, okay, where are going these hybrid edges now? So we'd like to have some kind of support for who is the recipient of gene flow, and some kind of support who is the donor of gene flow. So again, what we found that was helpful was to consider one hybridization at a time. So for each hybrid network and each hybridization in the network, we keep this hybrid node, but all the other ones that might exist outside, we remove them by removing the minor hybrid edge. And once we have a network with a single hybrid node, then we can talk about clades. So we can talk about this being the hybrid clade. So it's below the 2 parent hybrid edges. And then we have a major sister that is sister through the major hybrid edge, and a minor sister. So then we can say gene flow came from this minor sister, and we can talk about a clade here. And so this is, in my example here, 32 is the number of bootstrap network when A was the hybrid clade with sisters E and B. And in blue here, we have the support for exactly this edge as a hybrid edge. So from E as a sister to A as the hybrid. And 33% is the percentage of bootstrap network where it was exactly from B to A. So we can ask, okay, where are the others? So it's fairly low support, even if the tree, the backbone tree is always the same in all of our networks. There's a lot of variation in where is the hybridization. Only a third support for going from E to A. So what are the others? So we can look what proportion, who is the hybrid in all these bootstrap networks? And this is shown in red. So A is the hybrid in only 33% of the networks. In other networks, it can be E, with 12% bootstrap support, or the clade OE, 44%. So that's what we see most of the time. OE is the hybrid clade. And then where does it come from? So the minor hybrid edge, where does it come from? And most of the time it comes from A, actually, 49% of the networks. So it looks like in many of the bootstrap networks, gene flow goes from A to clade OE. Right? So there is uncertainty about the direction of gene flow, and if it's really E that's involved or the clade OE. So this is just to show that there are many questions we can ask about uncertainty in a network. We can ask about a whole edge. We can ask about just the donor. We can ask about just the recipient. And this example is fairly simple because the backbone tree was always the same, and there was only one hybridization. So it can get fairly complex, and this issue will have to be sorted out to be able to make sense of Bayesian methods for network reconstruction.
Wait, sorry. So what is the take-home message here? Is it that there's...
So my take-home message is just, it's really hard to summarize.
Right.
Here,
I mean, but I mean, are you saying that like our established way of summarizing this uncertainty is bad, or that like the inferential problem is just hard, and so the uncertainty is high, and so we get this spread?
Oh, the inference is hard in terms of where is the reticulation. So in the examples I've seen, there tends to be a lot of uncertainty about where the hybridization goes. But here I'm mostly interested in another problem, is how do we visualize this uncertainty? And here I needed to show the network twice to show different things. And then different colors to show this is about the hybrid, this is the recipient of gene flow, and this other color is about the donor. It's really not easy. So each edge has lots of different kinds of supports. Support for being the donor, or support for being the recipient, or support for being here, this edge, exactly this donor with this recipient. Lots of different things we can attach to the tree, and there's no standard way for now to summarize this uncertainty. Yeah.
Got it.
Okay, so this topic, I'm really excited about this. How do we use networks now? So we have them. Let's see if we can trust them. How do we use them for studying trait evolution? So I talk about a model for continuous response, a very basic model, and then how can we extend the model to test for transgressive evolution? So it's good to start from the basics. And on trees, a basic model for trait evolution is the Brownian motion model, where a trait goes up and down with just random drift, meaning has at each step, each generation, it can go up or down with equal probability. And then, at a speciation node, the two daughter species inherit the trait of their parent. So here, the gray species and the black species will start from the same value because they have the same parent. And then they each have their own Brownian motion independently of each other and going up or down. So that's the traditional Brownian motion for trees. And what we need that's new is what happens when the population is injected new genetic material from another here. So in this example, if this ancestral species got 30% of its genes from the blue parent and 70% from the orange parent, then it's natural to think that maybe the trait of interest will be a weighted average of the traits of the two parents, where the weights are the genetic contributions. So the weights gamma and gamma 1 for parent 1 and gamma 2 for parent 2. So visually, it would mean there is a Brownian motion evolution here, depending on the branch length, and also here. But at the time, right at the time of gene flow or hybridization, here we have our weighted average, and then the Brownian motion can continue. So this is a very basic model, a null model, if we want, that we can use later to test various hypotheses. And it's not new. It's been used for a long time on pedigrees. So on pedigrees, every edge is one generation. So branch lengths are 1. Here we have any kind of branch lengths. And then on pedigree, every individual has 2 parents. So every node is a hybrid node with inheritance gamma. Here we have different gamma values. But basically, it's a very similar model. Oh, yeah, and it makes sense for polygenic traits. If here we're looking at a trait that is controlled by many, many genes, it's natural to think that 30% of the genes, to expect that 30% of the genes controlling this trait come from one parent, and 70% of the genes controlling the trait are from the other parent. This model was also used more recently in a phylogenetic framework for allele frequencies. And it's a really cool paper. It's for the tree mix model. So here, I just want to highlight this is a cool model to use for comparative biology. Right? So we get, because we're using the Brownian motion, we expect traits that are normally distributed at the tips. And then we just need to have this covariance matrix between taxa. So that's the phylogenetic covariance. It's the covariance because of shared ancestry. We're used to this if we're doing comparative methods, where this matrix is just if we have a tree. So let's say we don't have this blue arrow here. If we have a tree, the covariance is just the shared time between taxa I and j. So let's say I'm looking at taxon, the red taxon here, I, and the blue taxon, j. The time that they shared is just this black edge. So the covariance matrix would be proportional to the time, the length of this black edge. If we have a network, the formula for this covariance matrix gets a little longer. And it gets more complicated because now if I'm taking taxon I and taxon j, I have to consider all paths from the root to each taxon. So if I'm looking at the green taxon here, this is a fairly simple network. It's just one hybridization, just 4 taxa. There are only 2 paths to this green taxon, one path here, another path there. So I have to consider all paths to go to that taxon. And so it makes this formula a lot more difficult. And certainly, this is not the formula we should use if we want to calculate this matrix. Because on more complex networks, with more hybridizations, there are many, many more paths. And this is just going to be intractable. But good news, there is a fast algorithm to calculate this covariance matrix if we consider not just the tips, I and j, but if we consider all nodes, and we can start from the root and calculate the matrix of this covariance matrix between all nodes, starting from the root. And just one tree traversal, and we can get this matrix. So this is nice. So we implemented this in PhyloNetworks package for networks, and we also extended this model to like we did for Pegel's lambda on trees. So lambda is a parameter that parameterizes the level of phylogenetic correlation. When lambda is 0, we have a model where all tips are independent of each other. No phylogenetic correlation. The tree, we just don't care about it. Or the network, we don't care about it. And lambda equals 1 means we have exactly what I described. And then lambda in between means that there is this network that causes correlation plus independent evolution across trees. So we can estimate the level of phylogenetic correlation for networks as well. So once we have this model, we can ask a ton of different questions. So one question would be, what is the phylogenetic signal of a given trait? Is the trait labile and with low signal, phylogenetic signal, or is trait quite conserved with high phylogenetic signal? We can ask, is a trait evolving way faster in one part of the network than in another? This is not something we implemented, but we can ask the question fairly easily. We can do ancestral state reconstruction using the network. So I'll be giving examples of this. We can do phylogenetic prediction, so it's really the same as state reconstruction, except that it would be on present-day taxa for which we don't have observations of the trait of interest. And then we can also do regression, so phylogenetic regression between different traits, or phylogenetic ANOVA if we have categorical predictors. So I'll give an example of that. And then the last thing that I would like to talk about is, can we go beyond this very basic model and allow for transgressive evolution? And then can we test that? So I'd like to use an example from a beautiful data set published in 2013 by Ray Kui and et al. And co-authors. It's a data set on these fish in the Gulf of Mexico. There are, as you can see, so they had a lot of genes. There's a lot of discordance, so there is incomplete lineage sorting going on and other things. So we estimated a network on these species. And we had 3 reticulations here, all of them with moderate inheritance probabilities, like 13%, 12%, and higher here, like 30%. And then we were interested in these 2 traits that were published also by Kui et al. One is sort index. So sort index, I should say, these 2 clades here are sword tails. So they tend to have swords. Most of them have swords. These are northern swordtails. These are southern swordtails. And then these are platyfishes. Those 3 species, they're in the south, and these other species in the north. And so they tend not to have sword tails. So sword index is the length of the sword divided by the standard length of the fish. And then female preference for sword, that was obtained using binary choice experiments. So females were given a choice. I believe it was mostly on screens, where they were shown a male with a sword, a male with no sword, and it was measured how long they associate with each male, and then we can calculate a preference for a sword. So this is the result of ancestral state reconstruction for both of these traits, female preference in red and sword index in blue. So sword index, let's start with that one. Sword index, that was available on all species. And then the ancestral state at the roots was fairly high, so it was inferred that the ancestor of all these species had a sword. And this is not new. This is what Kui et al. Found also. And basically, using a network does not change the conclusion. But it's good to know. It's reassuring, right? A phylogenetic signal was high for both. And I believe it's mostly because of these two big clades, the platyfishes and the swordtails, that are fairly different. And then for female preference, what's interesting is it's really hard and time-consuming to do these binary choice experiments. So there was data for about half of the species, right? Every species with a star here means that there was no data. No female preference was not measured. And so the number you see here is the phylogenetic prediction. So just like we can do ancestral state reconstruction, we can do a prediction for those present-day species. And because phylogenetic signal was high, these predictions can be informative. Right. We have them with prediction intervals are not shown because it would be too crowded. Phylogenetic linear regression is really interesting. So here we could consider the sort index and see if female preference, caused sort index to, maybe female preference caused selection for males to have a sword. Right? So we can do this regression here in the model. Y needs to be a continuous trait. X can be any kind of predictor. And then phylogenetic correlation is in the residuals here, in what is not explained. So if X has a strong phylogenetic signal, then we would expect Y to have a strong phylogenetic signal too. And it's possible that all the phylogenetic signal in Y is explained by X and that there is none remaining for the residual. So it's useful to have a lambda parameter here to estimate the phylogenetic signal in the residuals. Right, so we use this for sort index and female preference. So in black, you see the species that have data for both. And we found a positive association, but it was not significant. And again, qualitatively, it's the same answer that Hu et al. Obtained. So using a network didn't change the conclusion. And that's, it's reassuring, actually. Because, yeah. So that's cool. And then the last question would be, okay, we used a very basic model for trait evolution because we assumed that the hybrid trait would be just a simple average of the two parents, weighted, but just exactly the average. And this is a fairly strong assumption. So we can relax this assumption by saying, okay, there could be a shift. It could be something else than the average of the two parents. And on this, sketch, I made the shift really large. But what it means is that the shift can cause the hybrid species to have a trait outside the range of the two parents. We have the two parents, the blue parent and the yellow parent, and it's possible with this model that the trait goes outside of the other range. So we have this model, and then if all the shifts are 0 at all hybrid nodes, then that would mean that there's no transgressive evolution. If it's the same shift at all hybrid nodes, that could be what we expect if a trait is under selection and then a hybrid is given an advantage. And so maybe there is higher yield. That's for all hybrid species. So if the shift is constant, then we call this a single effect transgressive evolution. And the most general model would be to have variable shifts. So different hybrid nodes would have different shifts. And then we can use F-test to compare all these hypotheses. F-tests, it's nice to have them available because they're typically more powerful than likelihood ratio tests. But it's a simple linear model, so we can do that. We have a bunch of simulations where showing that it works. And then on this example, for sort index, we didn't find any evidence of transgressive evolution. So I'm going back here for sort index, the model where we have a shift of 0 at all 3 hybrid nodes was the preferred model. But for female preference, there was evidence of transgressive evolution and actually heterogeneous. So I'm going back again. For female preference, it was this model with variable shifts that was the preferred model. And so for one reticulation, there was a big increase in female preference for sword, and in the other two, fairly big decreases in female preference. So all the work that I did on this topic is implemented in the PhyloNetworks package. It has tools for reconstructing networks. It has tools for summarizing bootstrap values. I really welcome new ideas about this. If anyone wants to contribute ideas, I think we need that in the community. And then all the work on trait evolution. For now, most of what is in there is for continuous response, but we're working on discrete traits as well. And then we have a bunch of tools to plot networks and to manipulate networks, like rerouting them, extracting the major tree, calculating distances between networks, extracting display trees, and a bunch of things. It's a Julia package. If you haven't heard about Julia, it's really great. Check it out. So I want to thank my collaborators. Claudia Solis-Lemus was really the driving force for all the work to estimate networks. And then Paul Bastide did fantastic work to for the trait evolution models. Undergraduates helped a great deal too. And then I want to thank my collaborators who really provide the motivation for all this work. It's motivated by work on baobabs. And David Baum and Nisa Karimi are collaborators on this project on baobabs. So thank you, Eric.
Thank you very much, Cécile. That was a really beautiful talk, just in terms of content and in terms of presentation. So amazingly enough, one of our more senior audience members, Joe Feldenstein, has discovered a new way of asking questions as part of this. There's a live chat thing that is on YouTube. So he's already asked a question there, and feel free to ask there or on IRC or via Twitter. But I'll just ask his question, and it refers to one of your earlier slides when you were looking at the bootstrap support. And he said that in this example, the gene flow from A to OE is impossible as it goes back in time. Though I'm not sure, it depends on the branch lengths, I suppose. Do you want to, but anyway, I'll just continue with this question. Presumably your analysis methods allow that because they don't use rooted trees or branch lengths.
Yeah. So here there are two things. First, the network as it's plotted is not using branch lengths in the plotting. So the fact that, so it could have been plotted with this branch here being a lot younger. Just it's not using branch lengths. So yeah, if it was from A to OE, then we would have to have that this point in A older than this point in OE, and so this plotting would not be representative. It would have to be plotted differently. The other thing is that it depends. So our method reconstructs branch lengths in coalescent units, and coalescent units, I don't think that they correlate with calendar time very well. If there are big changes in the population size, effective population size, or in the generation time, then coalescent units would really not correlate with years. So I don't even trust the branch lengths that we get in coalescent units to be used for calibration.
Got it. Yeah. I mean, but it is still, I mean,
yeah, so here the plotting function just puts all the tips at the same time, and then any node from the tip would be one step earlier, and one step earlier, and one step earlier.
Yeah.
just the visualization here makes us think there is a problem to go from A to OE. This is just in terms of visualization.
But I mean, I guess the question could still stand, right? Like if for instance the clade going from A to D descended from O, that would give you a sort of time, right? I mean, that's saying that you. I mean,
I see. Okay. So, for example, if O is an R group, we want to put the root of the network here, and having hybridization from A to this point would be impossible. Agreed. Totally agreed.
Okay.
Yeah.
Yeah, I mean, I guess one of my questions was sort of related to this branch length thing, which is, I mean, I agree that there's issues of using branch length, and it sounds like the likelihood setup just uses the same departure from clock for every tree. But I mean, that's sort of an implementation detail rather than an inherent feature. I mean, I can imagine there being, maybe this is taken as an Bayesian land, but, you know, there being some parameterized departure from clock that comes from a distribution rather from a fixed parameter.
Yeah.
So it sounds really hard.
Yeah. But I agree with the Bayesian framework. If we can use branch lengths and use that to get more information about where the hybridizations are possible, that would be great.
I mean, I guess the same thing happens with, like, goes with rooting as well. I mean, I agree that there are situations where rooting can be problematic, but are you sure that the signal doesn't outweigh the noise?
There is one simulation study where comparing a pseudo-likelihood method using rooted triplet and a pseudo-likelihood method using quartets, unrooted quartets. And the method based on quartets was more robust.
Wow, it's amazing.
So,
quartets are just like totally making a comeback.
Yeah, it's surprising because to get a single gene tree, it's not the best way. Using quartets is not the best way.
Yeah.
Mm-hmm.
So Joe also, he makes one comment, which is the baobabs are not trees, they're themselves networks, which is astute.
This is great.
But also that coalescent trees can correlate with time if you include population sizes on branches. But I guess that would also, yeah, I don't know. I guess I would think of that in a Bayesian framework as well, but I guess there's nothing.
Yeah, can you repeat? I didn't get that.
Oh, the question, he just said coalescent trees can correlate with time if you include population sizes on branches.
Yes, correct. So that's where Bayesian methods are, I think, going to be really useful, because we can allow for different, for variability in rates, variability in population size and everything. And so that if we can use branch lengths using reasonable assumptions, it will be really useful to be able to, because we need those reticulations to be consistent with time. And so we can, if we can have time, then we'll get more information about those reticulations. I agree.
So the continuous trait stuff is really beautiful, and I'm just amazed that you were able to make this work at all. Though, I mean, there's a nit I have to pick, which is and it must be really hard if you haven't done this already, but it sort of surprised me that when you had the hybridization event, it like just merged the two, or just like took the average. Is there really no way to like condition, like have a Brownian process where you condition on those things being the same at the hybridization time? I mean, it's not sort of the same type of generative process.
But why would you want the two parents to have the same trait at the hybridization time?
Oh, I guess that doesn't make sense, does it? Because it's not like a coalescent thing. It's like there is a hybridization, which is a new, right?
I see. If we want to model geography, we would want the two parents to be at the same place.
But this is not that, yeah.
So that would be really useful model like this to condition on the two parents being in the same place.
You saved my question from being stupid. Okay, now I get it. Okay, so yeah, you have two parents they have two different, wing sizes or something. They'd have a baby, and this, yeah, there's some average plus some deviation, which is your delta. Okay, I'm gonna stop making a fool of myself and ask another question from Joe.
Okay.
He just says, excellent talk. It's great to see statistics finally used in these networks. Too much of the mathematical literature previously was non-statistical.
Yeah, but it's hard.
Yeah, it is.
I think that's why.
Let's see. Oh, yeah, one thing I saw a little bit later in your talk was, like in the application section to the fishes, there was a lot of inheritance coming from the ancestor. So you would, there would be hybridization with a couple nodes up the tree, which seems...
Yeah. Oh, this is a great question. Like this one here, I don't know if you have.
Yeah. And then what was also interesting is that when you were talking about your bootstrap thing, like this edge going back to OE, it seemed like those numbers were pretty far back. I mean, is there some bias somehow that's like pushing like these hybridization estimates deeper in the tree?
Oh, I don't know about biases. So this reticulation edge can only happen if there is some ancestral species that was either when extinct, that was still existing here and hybridized and then went extinct.
Yeah.
Or just is not sampled.
Yeah.
Didn't go extinct, but it's not sampled. So we have to have this extra species to be able to have a hybridization from an ancestor to a descendant. That's one issue. Is there some bias to put these? I don't know. I don't think that. So it's a fairly new field to have, and we don't have many simulation studies. And then it takes so long to estimate each network that it's hard to have the simulation studies.
Yeah.
It would be really interesting. What we did here is we needed a calibrated network. And we estimated branch lengths using a distance method, so using pairwise distances between taxa in the genetic data, and fitting the branch lengths to match the pairwise distances as best as possible. And it looks like the branches are estimated to be 0 here, so it looks like the hybridizations are pushed towards the present. I don't know why. Oh no, actually, I would read this to what Fabio Pardi and Céline Scornavaca have found about the canonical version of the network. There's still work to be done here.
Yeah, no doubt.
Things that we don't understand.
Okie doke. Well, I don't see any more questions. So thank you very much, Cécile.
Yeah, thank you, Eric. Thank you so much.
Yeah, it was really lovely. Yeah, so that concludes this trio of talks. There's going to be another trio coming up that's going to be about continuous traits. So we've got a bunch of really great speakers lined up for that. And there will also be a talk that we'll be talking about comparative methods.
Yeah, cool. That's great.
All right.
That's great.
Thanks.
Thank you, Eric, for a great series.